Assalamualaikum and hello everyone, and very good morning to Doctor. So this is our MATLAB project. We analyze dynamic response, open loop and closed loop of a DC motor. So we are from group V15. So this is our 5 team members: Aiman Hakimi, Ahmad Shafiq, Muhammad Zunurain, me, and also Nurul Najiha. So a little bit introduction. This project is to design a proportional controller in P controller, and it uses a non-inverting amplifier with a closed loop system. And the problem statement is, how does the value of proportional gain Kp affect the stability of the system and its steady state error, and how the performance of the controller design due to disturbance imposed. So the hypothesis of our group is that the proportional gain will control the denominator of the transfer function of the system, and it will alter the pole and consequently its steady state error and stability. Objective. The main objective, as proposed in the UKM folio, from the UKM folio, the main objective is to design proportional P controller that regulates the angular velocity of the motor such that it remains constant despite the presence of unmodeled dynamics, noise and perturbation. So there are 3 targets. The first one is the steady state angular velocity, which we want to reach 25 radian per second. And one steady state error, 20% or near that value. And we want a maximum overshoot that is less than 4%. So we go on to study the first model that we in our task.
Okay, my name is Aiman Hakimi and I will present for model 1, L1. So for the first part is tachometer calibration. I need to deduce the value of constant. So this is the equation of the tachometer output voltage is equals to constant Kt times with angular velocity of motor. So this is the diagram of our simulation. We input the voltage that is 15 volts, and we got the value of the tachometer output voltage of 0.126 volts, and angular velocity of motor is 1.529 radian per second. From these values, we can find the constant Kt as 0.0824. So now we need to find the time constant. Time constant when the motor is running 400 RPM. So 400 RPM is 42 radian per second. So we need to find the input voltage for 42 radian per second for the simulation. That is 411 volts. So I input 411 volts of input voltage. It will produce 42 radian per second. So this is true. So from the simulation, we find the VT tachometer output voltage to be 3.44 volts. So I plot XY graph of angular velocity of motor versus tachometer output voltage. So from this graph, I plot 3.44 volts at the x-axis, and I obtained the value of angular velocity to be 42 radian per second. So from this graph, this is correct. So from this graph, I also can reduce the constant Kt. It is the same 0.082. Next part is modeling DC motor. I input 5 volts to supply to the motor, and from this is the simulation, and I plot a voltage versus time graph. There is this. So based on this graph, we can conclude that this is a first order system. So since this is first order, I need to reduce the static gain Km and the time constant Tm of DC motor. So the equation of Km static gain is Vt times A. To find time constant, we need to find the Vt at 63% settling time. So the value is 0.026 volts. Then from the graph, we place the tracker of the oscilloscope at 0.026 volt to get the value of time. So we move the cursor tracker and the measurement shows that the time is 0.061 seconds. So the 0.01 seconds is the time constant Tm. Then I need to find E. E is 1 over Tm. Then with that we can get the static gain Km, that is 0.6852. We found the Km, we can present the general form or transfer function of G as equals to K equals to 0.6852 over 1 plus 0.061 S. So knowing that the input voltage is equivalent type amplitude 5 volts, the GS will be 0.6460. And by using Laplace inverse, the temporal equation, the motor speed is 11.233 exponent negative 1000 t over 61. Then we obtain the steady state speed of the motor, and the set time is 63%, that is 0.3211 radian per second. So that is all from part L1. Proceed to L2.
Okay, I am Muhammad Zunorain. I will be presenting model L2 model. Okay, in this part, we need to control the speed of DC motor. The principle is to approach as close as possible the value of set point we would like the motor speed to run to. We must minimize percentage error between input voltage Vin and the output voltage coming from generator tachometer. The first step is we need to build the closed loop system without the corrector to calculate the actual error of the system. We use a volt Vin that is 3 volt to have 750 RPM as reference point. Okay, the value of, we need to find the value of for resistance to have the equation of VE equal to Vin minus VT plus. Okay, we choose the value of R1 and R2 that is 1000 ohm, while R3 and R4 value is 500 ohm. Okay, while we already know the value of the four resistance, we put in this equation VE equal to Vin R1 plus R2 times R4 over R3 plus R4 times R1 minus VT times R2 over R1. We put and we get the equation that is needed. VE equal to Vin plus minus VT plus. Okay, for this section, we need to know the actual percentage error of the system we find. Okay, the value, the diagram above shows the value of VE that is 2.975. The actual percentage error is 0.833%. Okay, for the third step is we need to create a closed loop system with calculating suitable value for proportional gain that is Kp, such that steady state error is minimized to less than 20% as per requirement. Okay, in order to get the value of proportional gain Kp, we need to find the transfer function of the system. Okay, we get the transfer function of the system is 11.23 Kp over S plus 16.39 plus 0.926 Kp. The poles is we need to take from the denominator, that is S equal to 0, and we get the value of S equal to 16.39 minus 0.926 Kp. Okay, for this graph, we can find the value of Kp to know the it is stable or unstable. If we get the value of Kp more than 0, it will move to the left, so it will become stable. While if we get the value of Kp is less than 0, it will move to the right and it will become unstable. So the steady state error is this equation ESS equal to limit SES, where the ES is equal to RS minus TS, where RS is the step input. So the steady state error needs to be below 20%. So we choose 10% of the steady state error value. And we put the value in the equation, and we will get the proportional gain value is 1.42. So it is more stable because our proportional gain value is more than 0. So the next section, we need to know the value of RV to have the correct gain Kp when our value of R5 is fixed at 10 kilo ohm. So Vs is equal to 1 plus Rv over R5. Ve is equal to Kp times Ve. So Kp is equal to 1 plus Rv over R5. And we will get the Rv value that is 4.2 kilo ohm. So the value of Rv that is allowed to obtain less than 5% of error in practice. So we choose the steady state error that is less than 0.05. And we will get the proportional gain value that is 1.5044. So the block diagram is edited to the calculated value of the resistors that we get, and 175 volt of input voltage is set to get 25 rad per second. Okay, this graph is the angular speed of motor response from the oscilloscope. That is all for my part. Thank you.
All right, so for my part, in this section, we will take a look at how the controller that we designed in the previous sections work when it is subjected to disturbance at time more than 5 seconds. So below is the setup, and for the open loop control system. As you can see, the motor is subjected to a voltage of 245 volt and also a disturbance at time more than 5 seconds. And the input voltage is set to give an output of 25 radian per second. And as you can see from the oscilloscope reading, there is no significant disturbance that we can, that there is no significant ripple that we can see from the disturbance that we imposed. It goes to show that the disturbance is not strong enough to show any visible impact on the graph. And next, for the model L3B closed loop system, we will also use the design closed loop controller that we designed, and we impose the same disturbance of time more than 5 seconds using the calculated proportional gain Kp and other values of resistors that required in the summing junction. So as you can see from the diagram, there is a feedback system that we impose because this is a closed loop system. And for this, we only require 175 voltage because it requires, as you can see, it requires a much less input to adhere the 25 rad per second output. And we also input a proper resistance of R1 1000 ohm, R2 also 1000 ohm, and R3 and 4 500 ohms respectively, and R5 of 10,000 ohm. And we also input a value of RV that we calculated in the previous section of 4,200 ohms. And as you can see from the oscilloscope graph, with the final value of 25 rad per second, there is no significant ripple in the diagram. And we believe that even though we impose the system with a disturbance for time more than 5 seconds, it is not strong or visible enough to create a ripple in this graph. And that's it for my part.
Okay, Assalamualaikum. My name is Amar Shafiq. I will be presenting on using PID controller as the additional controller. PID controller is very famous in industry work where they use for various things such as controlling the water, the heater, and so on. So by using PID controller, we only have to tune the KP, KI, and KD. Okay, so to illustrate our controller, I have used MATLAB by coding it in a script. So here is our numerator and denominator. We are defining our motor transfer function, and this is our transfer function. So this is our sensor gain, which is Hakimi has gathered for us. The value is 0.082, and we make it in feedback. And here I set it, the KP is 1, which is similar to the original value, original response. And let's see what is the response for the original one. So here is the step response. We impose step response, and what we get is a steady state of 0.65. So this is the first order. So our PID controller is useful only to tune the KP value. So the KI and KD is useful for second order, which the integrator, it will increase our input closer to the steady state value, and the KD, it add the frequency to the overshoots to smoothen the edge. So here I have found out that I tuned the KP value to be 1.6 to get the 1, So our desired value is 1 for our step response. So 1.6 is the suitable one. So I have finished my part. Now we will go on to Haziq to present on conclusion. Thank you.
So for the conclusion, we have made it through the 4 models that we use. So for the first model is, although it's not very accurate, but we try to get the best which we could. So we use MATLAB software on our computer. Some of us could use MATLAB online, which also has the simulating function. For L2 model, in order to produce 25 radian per second, we need 175 volt with steady state error of 0.833%. And for the L3A model, which is an open loop system with disturbance, we forget that the 245 volt produce the 25 radian per second. The disturbance induced is unnoticeable. Next, for the L3B model, which is a closed loop system, we figured that 175 volt produce 25 radian per second. And also the disturbance induced is unnoticeable to affect the response. So for these 3 models, we got quite accurate 25 radian per second. So I think that is all from us. So thank you everyone for listening. We can see in the future. So thank you, Doctor, for also watching our project.